All right, 9.10 is Taylor and Maclaurin series. So this is going to be merging a couple of things we've done, the Taylor and Maclaurin polynomials with our power series that we were doing in the last section and writing them in a concise form. So we're going to take a look. Last time we focused on using the geometric series to find power series, and we ended up using this along with derivatives and antiderivatives. Here we're going to look at a general process, though, for finding power series for a function because they don't all work with the geometric series, derivatives, and antiderivatives. All right, so theorem 922, this is the form of a convergent power series. So if f is our function is represented by a power series, f of x is the summation from n equals 0 to infinity of a sub n, x minus c to the n, for all a in an open interval I containing c, then that a sub n value is the nth derivative at c divided by n factorial. So that says the nth derivative at c divided by n factorial. And f of x can be represented by f of c plus f prime of c times x minus c, f double prime of c times x minus c, and so on. So we're going to be doing derivatives, which reminds me that some of you still have some gateways to do, right? Yes, okay. Going to be doing some derivatives here. Okay, so my spacing here didn't really make this look very nice, but that's just the way it's going to go. So if a function f has derivatives of all orders at x equals c, then the summation from n equals 0 to infinity of x minus c to the n is going to take on the form f of c plus f prime of c times x minus c. And then if we merge together that a sub n that we'd had over here, right? This is where it's described, and we merge these things all together, it all pushes together to look like this. So we end up with each of the derivatives over their factorial value, right? So the second derivative is over 2 factorial, the seventh derivative would be over 7 factorial, and then it'd be multiplied by the polynomial x minus c raised to the power of that same derivative that we're working with. This is called the Taylor series for f of x centered at c, and if c is equal to 0, it's the Maclaurin series, just like we saw for the polynomials. Okay, so we're going to put it all together with some steps on how to do that for our last thing before we do some problems.
So what we did the other day was Taylor polynomials, and this is Taylor series.
Yeah, the difference is that Taylor polynomials terminated, and so we were finding things like this. It would say it's like a piece of 4, right? So we only found until we had the fourth derivative. Now we're going to do this indefinitely, and then write it back into a summation notation instead of being written in a polynomial notation. That's what we're doing. Yeah, good question. All right, so along those lines, the first thing we're going to do is we're going to differentiate several times and evaluate at c. So you're going to find f of c, f prime of c, f double prime of c, and so on. Once you recognize a pattern, you can stop. So there's not really like you always have to do 5 derivatives. Maybe you do, maybe you don't, but it'll kind of just depend on when you recognize a pattern. And then you're going to use that sequence, use the sequence developed to form Taylor coefficients. A sub n is the nth derivative evaluated at c divided by n factorial. And we'll have to determine an interval of convergence as well. And then we'll put the sequence together and simplify if possible. Okay, so I actually only have one example of these because they're so similar to things we've been doing. You're going to be like, I feel like I already did this because there's really only one difference, and it's at the very, very end, okay? The other example that we're going to look at comes from some tables that are in your book. So I know that at least Noah has the loose leaf book with him, right? So I can show you the table from that because I forgot to bring mine when we get to the second example. But the first example is going to look just like this series of steps. So we have a function, f of x equals e to the 2x. This has all orders of derivatives. Right over here where it says f has derivatives of all orders, it means you can take the derivative infinitely many times. So transcendental functions, trig functions, we have that ability to do so. Polynomials don't fit in this category, right? All right, so if we're looking at this Taylor series, or to create this Taylor series, the first thing we're going to do is take a bunch of derivatives. So we're going to find f prime of x, and I have 3 of them written down, so we'll see if we can stop at 3 and recognize what's happening.
Is it not a Maclaurin series?
It is.
Okay.
So it is because it's centered at 0. So Maclaurin is a more specific name for a Taylor series. They're all Taylor series. We call it specifically Maclaurin when it's centered at 0. So this one is a Maclaurin series, but general form or general name for it is Taylor series.
Okay.
Yep. It's kind of like, I don't know if you guys remember back from Calc 1, but, and I'm probably going to mess up which one it is, but there's a theorem called Raleigh's theorem. Looks like R-O-L-L-E, right? Looks like rolls.
Yeah.
Raleigh's theorem, and it's just a very specific case of, I think it's the intermediate value theorem. That's what's coming to my mind right now. And so it's not that it's not an intermediate value theorem problem. It's just that it collapses in a nicer way, so it has another name. This is much like the same thing. All right, so let's find some derivatives. So what's the derivative of e to the 2x?
2e to the 2x.
Mm-hmm. And what's the derivative of 2e to the 2x?
40 to the 2x.
Yep. And how about the next derivative after that? 8e to the 2x. Okay, so I think that's enough for us. So it's going to give us 4 values, and we're going to evaluate each of them, and it is at 0. So we're going to evaluate f of 0, f prime of 0, all the way down to the third. All right, so if we put in 0 into e to the 2x, what will we get?
1.
We get 1. What's the first derivative at 0?
2.
2. Second derivative? 4. Third derivative? 8. So it's just these coefficients, right? Because the e to the 2x part becomes 1 every single time when I put in 0. So these coefficients, these values are going to become the coefficients. So it's written on the previous slide, so feel free to flip back to your previous page if you need to write it down. But this is the first value, f of 0, is going to show up first. And then to this we add the derivative value, that's 2. And it should be times x minus c, but our c value is 0, so it's just x. Okay? And then we have the second derivative value, that's 4. And the second derivative is supposed to be divided by 2 factorial and multiplied by x, well, it's supposed to be x minus c, so x squared. It would normally be x minus something else and then squared. What would my third one be?
8 over 3 factorial times x squared.
Right. Okay. What we'd like to do is recognize or try to find a formula, right, that this is following. So the n factorial in the denominator is easy enough to spot, right? It's just increasing by 1 every time. And this piece is easy enough to spot. It's x to the n. It's typically speaking, it's the numerator value that we're trying to figure out what pattern it is. So we're looking at these coefficients that we have that came from, highlight them, they came from up here, right? I have a 1, 2, 4, 8. What kind of values are those?
Powers of 2.
They're powers of 2. Now, depending on where they start and so forth, we might have to make some adjustments. So it's a 2 to the n of some sort, and it might be 2 to the n. It also might be like 2 to the n minus 1 or something like that. So as long as you recognize what kind it is, then you can make the adjustments so that it starts in the right place. On this one, it really is just 2 to the n, and it works because if I put in 0, I get the first one. If I put in 1, I get 2. If I put in 2, I get the third one, which is the 4, and so forth. So it is 2 to the n. If you'd like, you can combine these at the end so that instead of it saying 2 to the n and x to the n, it just says 2x to the n. It's a little bit more concise. Neither one's right or wrong. I mean, they're both fine. So neither one's better than the other, I should say it that way. So what this is that once we've put it into one of these forms, it means that I can show what the summation is. So this is the series. It's the summation from n equals 0 to infinity of, and I'll use my second one, 2x to the n over n factorial. It's not much different than what we've done before, right? We're just looking for the pattern at the end and we're writing it in summation notation. Yes?
How do you take into account when n is 0 and it has 0 in the denominator?
Oh, because 0 factorial is defined to be 1.
Oh, really?
Yes, that's a definition for factorials
Okay.
that you probably haven't thought of in a while. Yep,
Okay, that makes sense.
it's a good question. Okay, any other questions? Okay. In your textbook, or on your textbook, ebook, whatever, on page 674, there is a table of power series for elementary functions. So we're going to let you guys go ahead and get out whatever device you'd be looking up your textbook on, or inside the textbook, or if you don't have it, take a picture of Noah's or something like that. And we're going to take a look at page 674.
674, you said?
Mm-hmm.
Mine's just in a binder, so, and I just put it in the little pocket. So,
I checked the problem that I emailed you about.
Mhm.
The answer key is just wrong.
All right, page 674 shows some elementary functions and their power series expansions, right? So the one that we want to look at is the one that we can find that most closely resembles e to the 2x. So what would that be in this table?
E to the x.
There's an e to the x. And I believe the e to the x says something like this. 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. Yes?
Yes.
It looks like that. Okay. So what we do is we identify our function with this one and we make appropriate substitutions or adjustments. So instead of x, we're going to have 2x. So everywhere we have an x in this expression, as it's written out, we're going to change it and we're going to have 2x. So this is our e to the 2x now. And everywhere there's an x, I'm simply replacing it with 2x. And the end result, also in that table, tells you that the summation from n equals 0 to infinity is supposed to be x to the n. So now ours is 2x to the n, still over n factorial. So using this table is a really direct thing, right? All we need to do is we need to move forward and we need to be able to change the variable for what our variable, not variable, but whatever's different, we need to make an adjustment to accommodate for it. And then we are finished with that. Okay? Any questions? Okay,